So you've seen already the distribution. It's not exact because, again, a couple of grades I'm missing, but even here, well, you don't know the average for the last year, but I do. So last year it was 32.60. This year it's 32.63. It's always very similar from year to year, and the pattern is always the same. Again, you don't know, but I do. The grade for the first exam is usually higher, then second exam goes a little bit down, but if the pattern remains as it used to be for years, the grade for the third exam should go up again, and that's related to a very simple fact. Material related to exam 2, heavily based on material related to exam 1. Geometry, trigonometry, vectors, forces. So, but the material for exam 3 is not so heavily based on material of exam 1. Less geometry, less vectors. So, so please keep entering your answers. And again, I recommend using internet communication for your preparation. You don't use it practically as much as any people before. Not sure why. And that's what we're going to start. Right now, before I just want to address the feedback. Always thankful for the feedback, and again, it will be posted on Blackboard so you can read. There is no personal information at all, and I'm not going to go through all. First of all, much smaller number, which is again absolutely a standard situation, and the majority of feedback related to the test say it's been fair, and that's what matters, because if everybody else hates it but doesn't say anything, it's like not voting. You can think anything you like, but if you don't go, don't act, you don't exist. So TFs, again, positive and negative responses, and again, I want to say the same thing I've said before, like here in this class, people have a very different background, so true for TFs. For some TFs, this is the very first course they teach in the whole life, for some not. And if you feel like your teaching fellow is not really prepared to help you the way you want to, you not just allowed, you're supposed to say something to him. And to me, of course, but if you do it to me, you should put a name and specific example, not just, I feel like my TFs may not be always prepared. Well, you know, there's a saying, you can bring a horse to a water, but you can't make it drink, right? So I can give an opportunity to start doing homework as soon as possible, but I can't make anybody to start doing homework as soon as possible. Same with teaching fellows. They have an opportunity to practice a week before the lab. They have that opportunity. And what you should say, if, well, did you practice? I don't feel like you helping me a lot. It's like a between adult conversation, right? Now, again, a note about pace, slower, faster. Pace, speed, time, very different for different people, because that's a very well-known fact. Different people perceive those kind of absolute matters, but differently. Yeah, time flies, or time gets still. When we say that, it's happening here, not around us. So someone said that I wish the amount of work would have been reduced. It was, but it was reduced to the minimum. It cannot be reduced anymore. One of my many responsibilities is to keep integrity of this course, to be at the same level as the fall or spring courses. And thank you. And this is very interesting. Much better this. That's it. Then what? And this I like specifically because a very common situation I've addressed usually on the first day. A student writes that lecture might be challenging because I jump around, and I do. I do it on purpose. And relative to many situations where people jump around, that actually makes me feel unique. Yes, my logic might look like a zigzag, but if you think that everybody else outside always uses straightforward linear logic, you may be surprised in your life. So think of this as a certain exercise which might also be helpful in the future. Well, and of course, if you have any questions or suggestions, you always can send an email. If you want to be not known, anonymous, you can use Piazza. It allows you to hide your name, wherever. Now, this is a recommended deadline. And right now, you're supposed to be able to see all 4 parts of the homework. So you can compare how much of that material might be still related to forces, vectors, and how much of that material is not related at all. It will be related to, like, some other type of trigonometry, reading functions and reading graphs in the future, but still much less right triangles. And all right, before moving on, let's see. Again, a very, very similar distribution. Well, we're going to start talking about oscillations. Or more specifically, a type of oscillations or type of periodic motion, which we call simple harmonic motion. You've seen examples of this around every day. These 2 types of motions have been used originally to build first kind of clocks and watches. This looks like a pendulum, but actually it's much more fun if you do it like this. This is a very standard simple harmonic motion. Horizontal one, but we can also have a pendulum like this. This pendulum has a name, a simple pendulum, or this, a simple pendulum when the mass is concentrated or can be replaced by a single point, single dot. This, something like this, is a physical pendulum. There is some mass distribution. But still, we can see for every object like this, the motion repeats itself periodically. So any motion like that, or like this, or like this is the vertical periodic motion. Oops. Every motion like that, they all have in common the point of a stable equilibrium. What is a stable equilibrium? Well, it's a location where if object is released at rest, remains at rest, but if we move an object away from equilibrium, there is always a force which points back toward the equilibrium. So that force tries to restore the equilibrium. So right now here, the net force, well, right now here we have elastic force because of the spring, force of gravity because of the earth, and applied force because of the fingers. So that if I let fingers go, elastic force will be stronger than force of gravity, and net force points up. But when object reaches equilibrium, it doesn't stop there. It goes through the equilibrium. And in that case, the net force points down, so the force constantly changes its direction. Same, say here. Well, in this situation, it's easier to talk about torque than force. There's a torque which constantly tries to restore equilibrium. And here and there, why do we call it stable equilibrium? Well, because there is also unstable equilibrium. In this situation, when we deflect the object from equilibrium, the force doesn't move it back to equilibrium. It starts moving farther and farther away from equilibrium. So it is in equilibrium, because I still can make it at rest. But as long as I deflect it from equilibrium, that is the system getting broken. So all those systems, all of them, have this very important state or location in common, which makes our life much, much easier. We don't have to solve all these problems again and again and again. We can solve one simple problem, and then that solution we can apply to all these situations, because that solution will work for all those situations. And of course, the easiest case is a horizontal motion of an object attached to a spring. And well, here we actually have two springs, so still kind of too complicated. That's the easiest situation. One single spring, gravity and normal cancel each out, there is no friction, so the only force which might act on this, well, weight of certain mass is elastic force. So if I compress the spring, the force now will be acting to the right. Why is it not moving? My fingers, of course, cancel that force, but if I let it go, that force starts moving the object to the right, but it doesn't fly away. Eventually, it stops, and then restoring force pull it back to the equilibrium, but it doesn't stop at the equilibrium. It passes the equilibrium, and this motion, well, under ideal circumstances with no friction, would be happening forever. This is the type of the motion we want to study first. And of course, well, we're going to start from properties of a single spring. So I want to ask you this question. What do you think? This is a snapshot of that very system. The snapshot shows a ball at that location when elastic force acting on the ball points to the right. So the question is, where do you think is the location of the stable equilibrium? So while waiting for your answers, how would we study the property of elastic force? Well, we know that we have a device we could use to measure the amount of that force, a spring scale, or we call it a dynamometer. So I can stretch the spring and read the magnitude of the force. All I need to do is just now take a ruler, measure length, and plot a graph. But this is not very convenient system because, well, right now I need at least two more hands, one for the ruler and one for writing down data. So instead, we have a much easier system which we can study. A vertical spring with a weight. So a free spring, of course, has a certain length and, of course, has a certain mass. But first of all, we neglect the mass always. And what important is not the actual length, but how much longer does it become if we pull. And if I pull on this string, I'm not sensitive enough to know how many newtons do I apply. But if I attach a weight, 100 gram weight, 100 gram weight means force of gravity is about 1 Newton. And I can see that the spring has stretched by this amount. I can attach one more weight. So now the force is doubled. If I ask you, do you think the length of the spring is doubled? What should you say? No, not the length, the elongation, how much longer it has become. This distance is doubled. So we can repeat this experiment more times, and here the answer is, what do you think? Of course, it's supposed to be somewhere here, because this force tries to move it back toward the equilibrium to the right. And here, what we can do, well, let's say 1 Newton. 1 Newton. 1 Newton. The elongation, not the length, yeah. Well, let's say it was about 10 centimeters, 0.1 of a meter. 2 newtons, the elongation, 0.2, etc., etc. So we can plot the graph, connect the dots. This is the graph for the magnitude of the force as a function of the elongation. That works backwards. If we contract the spring, you see these vertical bars, delta x is this. But if we use absolute values, we can make the same measurements while contracting the spring. We're going to get exactly the same results. And that's a linear function. And for the linear function, we know in mathematics, well, first of all, it goes through the zero. So y-intercept should be equal to 0. There is no y-intercept. So for the linear function, we should write something like this. Well, in general, m delta x plus b. M is the slope. B is y-intercept, supposed to be equal to 0. And when we talk about springs, we don't use a variable m. From historical reasons, we use a k. We call it spring constant or force constant, and this equation has a name, the Hooke's law. He has described it first. This equation relates the magnitude of the elastic force in the spring and the elongation or contraction of the spring. This is basically a definition of this new variable, spring constant or force constant. This is how we can measure it. A Newton over a meter, the natural unit has no name, just a Newton over a meter. Now, so this graph is a straight line, doesn't go backwards. Magnitudes can't be negative. But of course, a real question is, what would be the graph for the x component of the force acting on this object as a function of its x coordinate? First of all, there is a difference between using this symbol, delta x, and this symbol x. X is the reading. That's what we read. And since we can choose the origin anywhere, depending on how we choose it, the reading will be different for the same location. So, of course, we make our life as simple as possible. We always, if we can, choose the origin at the equilibrium. In that case, x and delta x become same thing. So here, this is a ruler. Again, positive numbers go to the right from 0, negative numbers go to the left. So now, this location described by a negative coordinate, 0, positive coordinate, and we know a force is a vector, so a force also has a component, and if force points to the right, the component is positive. If it points to the left, the component is negative. That means this graph, the x component of a force as a function of location, might be different, maybe not. That's what I want you to do right now. Please, sketch a graph. What do you think? How would it look like? The graph for the magnitude as a function of absolute displacement looks like this. And the equation for this line is a linear equation, standard linear equation with 0 y-intercept. The slope represents the spring constant, or people call it force constant. What about the relationship between actual x coordinate and actual x component? This is the part which technically is based on what we've learned during week 1. Yeah. And of course, the easiest approach would be draw 2 pictures first. Well, one picture actually is already given for an object to the left to the origin. And another picture would show the same object to the right, to the origin. And origin right now is at the equilibrium. So that should tell us how the force should be directed. And here, for this particular picture, the x component of the force is, how do we finish this sentence? Negative. The x component of the force is what do you think? If you think the x component of this force relative to this axis is positive, please raise your hand. If you think it's negative, please raise your hand. Nothing new. How does it point? How does this vector point? Positive, same direction. So the x component for this force at that location, at that instant, is positive. What about x? This number we read Positive or negative? What do you say? Negative. How do you know? It's to the left to 0. That's a standard number line rule. To the left to the 0, numbers are negative. So that already gives us a hint. If I write this equation, fx equals k times x, would it be a correct equation? What do you say? You say no. Why?
X is negative. This is still positive.
That is correct. This is a spring constant, a fixed number, like a mass, always positive. You need to take this number, multiply by something, and get this. And we just said, here and now, that's supposed to be a positive number, but here and now, this is a negative number. So how do we fix it? Put a negative sign. That's a fix. Now, of course, we can repeat the same reasoning. Let's say the, I'm going to draw a new picture. Let's say that the ball is here. That's the origin. Positive numbers go to the right. And this is the new value of x coordinate. Is it x? This x, positive or negative? Positive. It is to the right to 0. Now, what about the force? How does it point? The force must point toward the equilibrium. The equilibrium is to the left to the ball, which means the force has to point to the left. That's the force. Now, if we look at this vector, the x component of this force is, how do we finish this sentence? Positive, negative, or 0. The x component of this force, arrow points to the left, axis points to the right. The x component of this force is negative. So if I want to relate the x component of the force and the x coordinate of the ball, can I use this equation? No. Again, they don't match. This is positive, but that has to be negative now. What's the fix? So the equation for the x component of a force relative to the x-axis as a function of a position is this. Now, of course, if we take absolute values, we get this equation from that. How does a graph looks like? So a negative. So negative numbers make it positive, positive numbers make it negative. This is the graph. Again, it is a straight line with the same slope, technically, but now it goes both ways because the ball can travel left and right. Any questions? Yes. All right. But feel free to ask any questions. So, please solve this problem. Pick an answer, enter. Let me show you one more time this experiment. A free spring is being stretched by applying a force due to gravity. Well, force of gravity acting on the weight is acting on the spring. spring is acting on the weight. But in equilibrium, all those forces must have exactly the same magnitude, and 100-gram weight stretches the spring by about 10 centimeters. That's it. So we can use this experiment to calculate the spring constant, the force constant of this spring very accurately. And then we can use it to describe oscillations which might be happening with this weight or any other weight attached to this spring. And of course, whether we like it or not, it's still about forces. So we have to draw a free body diagram. As long as we talk about forces, we need a free body diagram. And I always recommend to start from drawing a free spring so we can compare what's happening to it. We can see what's happening to it, compare initial and final. This is delta x. This is delta x, the stretch. Now, what does that mean, this variable fx or this variable f? In general, in this situation, we can show several different forces. There is force of gravity acting on the weight. There is a force acting from the spring on the weight. That force has a name, elastic force. And there is also a force acting from the weight on the spring. That force actually has a name. Anyone? The apparent weight. Doesn't matter. This variable, this letter, what does that letter represent? Which force? Elastic. That's what have to be remember. It is a force acting from a spring. But of course, everything is in equilibrium. mg is equal to elastic. That's the Newton's second law for the block. The force acting on spring is equal to elastic. That's Newton's third law. So they're all the same. And so what's your answer? We only need to be careful with units here, right? We cannot use grams. We cannot use centimeters. So spring constant should be equal to force over elongation. Force equals to, in this situation, mg. That's going to be m 0.1, g about 10, delta x 0.1, 10. It's not a tricky problem. It's a review problem. We've used Newton's second law and Newton's third law as we've done it before. For a slightly different force, elastic force, just to study the property of it. Why? Well, we're going to use it later, right now. Now we can describe the motion. This is a snapshot. For this snapshot, we can write the Newton's law, and we can write the Newton's law for any situation. Yeah? First of all, relative to the vertical direction, normal force and force of gravity cancel each other out. That's why we start from studying horizontal motion. We neglect friction, so there is only one force which is responsible for the acceleration, elastic force. On one hand, the Newton's second law says this: at every instant, at every location, F net equals ma, and relative to the x-axis, F net is equal to F elastic, nothing else. However, we also know the Hooke's law says this. We just need to remember we write x, not delta x, because this is equilibrium. We choose the origin at the equilibrium, always, or almost always, every time when we can. So now equation says if left hand parts of the equation are equal to each other, that means right hand part of the equation equal, we can solve it for the acceleration. Acceleration is equal to this. That's it. And that type of equation works for any simple harmonic motion. For anything, any system, we can write a similar equation. So we just need to know how to solve this equation. Well, first of all, this combination cannot be negative. The mass is positive, K is positive. And for many different reasons, this combination is said to be equal to omega squared. Right now it's just a letter, but soon we will learn it's actually angular frequency. So this is how people write the motion. This is the motion equation, dynamical motion equation, for the simple harmonic motion. Works for all possible situations. The problem is it's hard to solve. Because acceleration is a change in the velocity over change, and another change in the velocity. So this is the equation we have to solve. And people do that in 211. It's much easier to solve this equation using an analogy, very common approach. When people use an analogy between simple harmonic motion and another very well-known periodic motion, circular motion. For every simple harmonic motion, we can find a circular motion with exactly the same period. 1 Mississippi. That's one period. So this is too fast. This would have been too slow. All right. So all I need is just practice. That's it. That's all I need. So these two motions are different, but they have something very simple in common. The x-coordinate is the same. If we look at the y-coordinate, it's different. It goes up and down, up and down. But the x-coordinate is the same. So if I want to describe simple harmonic motion, all I need to do is to describe the x-coordinate of a ball. What do we know about circular motion? There is one word which answers this question. What? Everything. So by transition property, now we know everything about simple harmonic motion. We just have to write it down, of course. Two questions we need to answer. How do we relate the radius of this circle, the instantaneous angle, and the x-coordinate? What equation should we write down? Which means what function should we write? Should we use sine, cosine, tangent, cosine? So this question answered x is equal to r times cosine theta. Now, what selection should we make to answer the second question? For the circular motion, uniform circular motion, what equation should we use for the angle? What do you think? For the uniform circular motion, what equation should we use? First one? What's wrong with it? It doesn't describe motion. It describes the fixed location. The angle is just some number, et cetera, et cetera. So what do you choose? Which number? Which equation? Yes? Hmm? Uniform means there is no acceleration. So we could have added more and more zeros here. That actually would make things worse because we would have to spend extra time for nothing. So the equation for this is the motion equation for the uniform circular motion. And all we need to do now is put these two equations together. One comes from the geometry, second from the properties of a uniform circular motion we've studied before. And that's what we have in the end. Now, a disclaimer. In geometry, we always can rewrite a cosine into a negative cosine. We just have to fiddle with numbers inside the argument. How do we do that? We don't care. We just need to know. It's possible. Next disclaimer. In geometry, there is no difference between sine and cosine. We can always convert cosine into sine and sine into cosine. How? We don't care. We just need to know that there is no difference. So in geometry, geometry tells us that any equation like this is a motion equation for a simple harmonic motion. It could have been a cosine, could have been sine, could have been some numbers outside or inside. It does not matter. Any equation like this technically can be manipulated into a cosine with a positive coefficient. That's it. That's the equation we're going to study because we have derived that equation. But all other equations also represent simple harmonic motion. So in general, an equation for the simple motion equation for simple harmonic motion might look like this. Some number times some function. Inside the argument, we may have a combination like this. We may have some additional number outside. Some numbers are more important, some numbers are less important. We'll talk about it in a second. First, this is how we write this equation when we talk about rotational motion or circular motion. That's what we call radius. This is what we call angular velocity. When we talk about simple harmonic motion, we use the same variables differently. First of all, we don't call this angular velocity anymore. We call it angular frequency. And we don't use R. We use A, because it's not the radius for us, it's the amplitude. We just used this analogy, and now we forget about it. What we see is this. For every simple harmonic motion, the motion is happening between certain limits. These are limits. So there is maximum displacement from the equilibrium to the right to the equilibrium. There is maximum displacement from the equilibrium to the left. The magnitude of that maximum displacement, that's what we call the amplitude. Mathematically, it is represented by the radius of that invisible circle. Equilibrium, maximum displacement from the equilibrium to the right. Maximum displacement from the equilibrium to the left. And this distance traveled from the equilibrium to the maximum displacement, that's what we call amplitude. And it is distance. A position might be negative, positive. For the amplitude, we take the absolute value of that. Of course, the amplitude depends on, well, how we stretch the spring. We can stretch it just a little. That will be the amplitude. We can stretch it a lot. That will be the amplitude. That's it. So now we can so make a note what might happen if the equilibrium and zero are not at the same place. In this example, zero is shifted. Why would we do that? I don't know. Don't do that. But if by any chance that happened, that means the motion is still the same between two limits, still same amplitude. We just count coordinates, not from zero, but from this number. And the equation just has an additional number. And of course, if we see that equation in our mind, we can always redraw the axis and make this number E disappear, make it to be equal to zero. Well, again, this is the summary. This is how we can describe any simple harmonic motion. Yes?
So we're only using E if our origin is not the same
With equilibrium.
as our...
Yep. Well, technically, we also use the same E when the origin is at the equilibrium. It's just E will be equal to zero for that situation. Normally, we can ignore it. It's not very important. What important is amplitude and the angular frequency. Other variables are just a matter of how we look at it. When we start the stopwatch, where we start measuring x coordinates, and all those variables basically up to us, we always can change those. We can choose when we start time. We can choose how we place the ruler. So only these variables, amplitude and angular frequency, really describe the property of the system. This is, again, what we just have learned and can be used right now for solving different problems. So a period, it's time for one complete oscillation, not a revolution now, oscillation. And again, let's say I move it here. How do I measure period? Well, I release the cart and I start the stopwatch at the same time. Click. Now I count how many oscillations it makes, let's say in 10 seconds. And then, if to calculate the period, I divide time to the number of oscillations. Again, frequency is the number of oscillations per second. Same relationship. This variable now has a different name, angular frequency. It means number of oscillations per 2 pi seconds. It's related to the period again. This combination has a name, a phase. Different oscillations have different phases. Young phase, old phase. This we call the initial phase, and then we're growing up. Or not. This number has no serious meaning for us, just a name. This number has a very, very serious meaning for us. And in general, I would recommend, play with graphs. You have a graphic calculator, or you can find a graphic calculator online and play with graphs, see how things depend on those variables. For example, this number shifts the graph up or down. If E is 0, so the middle point is here, and the graph goes like this, up and down, up and down. Period. If you increase the period, it makes this graph wider. You stretch it. It takes more time to reach the same position. If you increase the frequency, what does it mean? If you increase the frequency, you decrease the period. You squeeze the graph. It starts oscillating faster and faster. It takes less time to come back to the initial position. What about amplitude? What does it do? Well, if you increase amplitude, that means you increase those limits. The span is not this anymore. It's like this, which means the graph gets stretched in both directions. That's what it means. Question? You see a portion of a graph. Under ideal circumstances, this graph wouldn't have no end, no beginning. Yeah. The motion would have been happening forever. From negative infinity to positive infinity, from Big Bang to we don't know what happens. But we take a snapshot. These are numbers we know. So, for example, if I look at this graph, I can say something about amplitude. I can say something about this number, E. Period, that's what I'm asking you for. Frequency, angular frequency. These are all immediate variables we can extract. And as the result, actually, we can write the motion equation. The motion equation describes how position changes with time. So, for the amplitude, what do you think should be right here? Amplitude is the magnitude of the maximum displacement from the equilibrium. This is a graph, a mathematical abstract, but I could draw a motion diagram. I could look at the moving object and make several snapshots and put them together. So I would actually see how the object would have been moving. It reaches, so it's here, then here, then here, reaches maximum displacement, reverses its direction, travels back, reaches maximum displacement in the opposite direction, and it starts traveling back. This is, we usually call xm. This will be negative xm. Now, equilibrium. Do you think it's set at 0 or not? What do you think? What number do you think can we write here? Here. 6, exactly. Because we can see that these segments are equal to each other. So it goes 6 meters both ways. So that should be 6. That should be negative 6. That should be the equilibrium. So what do you think? It is 0 or not? 0. Yeah. Otherwise, the graph would have been shifted. One part of the graph would be kind of larger than another. 0, not amplitude. Amplitude is not 0. What number should we write for the amplitude? 6. 6. That is correct. Now, what did you say for the period? 8 seconds. So I always recommend for any graph, start looking from the smallest part of the graph, which is a quarter. How many quarters in one period? That's why we call them quarters, right? So if you know the length, the time for the quarter, you can calculate period, a half of a period, everything. So here we have 2 quarters, 1 quarter, 2 quarters, and a period is equal to 4 quarters, so 2 times 4, 8 seconds. Frequency, 1 over a period, 1/8. Now for the frequency, we have several standard units. First of all, 1 over a second, which people sometimes write like this, second to the negative first, using scientific notation. But also, when we talk about frequency, people use Hz, hertz, same unit. Angular frequency, well, 2 pi regular frequency, which gives us whatever number it gives us. 2 times pi times 0.785 around, well, 0.785. For the angular frequency, like for the angular velocity in the past, we should write radians per second. And now we can write the motion equation here. The motion equation here, well, we have to choose what function do we want to use. In this situation, the choice should be clear. Yeah? What function do you see? What is it? Sine, cosine, tangent, square root, parabola? You say all to all. Yes to all? First of all, it cannot be parabola. It cannot be tangent. The only functions we can use are like this. So the only choices we have to make is between sine and cosine, period. Yes? What do you say? Cosine. And here it's very helpful to refresh properties of sines and cosines. A cosine of 0 is 1. Cosine of 0 is 1. Sine of 0 is what? 0. So this is a very helpful information to make a choice. If it is not 0, if it doesn't start from 0, it cannot be sine. Now, technically, the function also depends on the initial situation. If I move it to the right, my initial coordinate is positive. And then it starts moving from positive to 0, negative, we're back. If I move it to the left, my initial coordinate will be negative. I have to know that. And then it becomes 0, then positive, then 0, then negative again. So here, my initial coordinate is positive. So my equation should look like this. A cosine omega t, no other function, no other constants. They zeros. E is 0, initial theta is 0. And so in numbers, it should be 6 cosine 0.785 times time. This is the motion equation. The motion equation, when it's done, must have numbers for everything but time and x. Those are running variables. All others should be numbers, specific numbers, like 0 here, for example. And of course, now we can use this equation to calculate the location of this object at any time. We just have to plug in the value for time. So, please calculate the x of 2. So x equals 6 times cosine 0.785, good memory, times time. Please tell me your number. 5.9977. Please tell me your number. Okay. Everybody who has the same number, please raise your hand. Everybody who has a different number, please raise your hand. Well, this is a situation when the majority is wrong. This is the graph. 2 seconds is here. What is this supposed to be equal to? 0. It's at the equilibrium. How did you get 5.9777? You plugged the numbers into the calculator. You press the equal and you read it. And it's wrong. The question is, what might go wrong? What mistake had been done so we wouldn't make the same mistake again? What do you think? Yes? Exactly. You've been using degrees all the way up to now. But omega requires radians per second. Time requires seconds. So the unit of this number times 2 will be radians, not degrees. You have a choice in a situation like that. You can switch your calculator from degrees to radians, or you can use conversion factor first. You convert radians to degrees and then use the number. And now you shouldn't have exactly 0 because this is some approximation, but you should have a number close to 0. All right. Calculate the spring constant. If so, 100 grams should be converted into kilograms, and the spring constant, mass, and angular frequency are related. So to calculate the spring constant, all we need to do is just use this equation, 0.1 times 0.785 squared. It's a very weak spring. Wherever it is, that's the answer. Moving on. The motion diagram. It's very helpful to be able to visualize what's happening. So again, in this situation, this is a special case when 3 conditions are used. First, The origin is at the equilibrium. Second, we release it from rest. And third, the initial position is to the right to the equilibrium, like this. We know that in this situation, the equation is given by that expression, very simple, amplitude times cosine. So the motion equation, well, it starts here, and it goes here, 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 here. That's the motion diagram, correspondent motion equation. Why do we need it? Well, for the motion equation now, we can plot a graph. A graph is not a photograph. A graph is abstract mathematical representation of the location of an object at different instances at t equals 0. The initial location was at x equals a. And when time was running, the x-coordinate was closer and closer to 0. Of course, the car doesn't stop there. It keeps traveling and reaching maximum displacement on the other side. After that, it goes back to the origin. After that, and this is exactly one period, and it keeps repeating itself again and again. So that's kind of simple. What about velocity? Where does the velocity graph begin? We release it from rest. So the initial velocity equals what? 0. And in the fraction of a second, the car was traveling to the left. So in a fraction of a second, velocity will be negative. So the graph for the velocity as a function of time, in this special case, begins from 0, then becomes negative. Eventually, the cart stops. When does it happen? In exactly of a quarter of a period. When it reaches, a half of a period. This is the maximum. This is the maximum, and it stops again here. When it travels through the equilibrium, when x is 0, speed reaches maximum possible value. After that, it is slowing down. So speeding up, slowing down. Then again, speeding up, slowing down. That's how it's happening with velocity. And speeding up for the first quarter of a period, slowing down for the second quarter of a period, then speeding up for the third quarter of a period, and slowing down for the last quarter of a period. Well, what equation do you think should we write for the velocity? What function should we use? Sine or cosine? Sine. And positive or negative? Negative. So the equation for the velocity is this. There's some maximum speed, V max. And probably tomorrow we will prove that the maximum speed is equal to this. That's it. We could just measure it. Yeah. But we will be able soon to prove it mathematically. A is the maximum displacement. Omega is the angular frequency. If we multiply them, that gives maximum speed. What about acceleration? For the acceleration, actually, easiest way using that equation we've derived. acceleration is equal to negative omega squared times x. That's it. Graph for position looks like this as a function of time. So how do we get the graph for the acceleration from the graph for the position? We have to multiply it by a negative number. So all positive numbers become negative, all negative numbers become positive. That's it. So acceleration does change. But acceleration, velocity, position, they all change with exactly the same period, frequency, angular frequency. Well, this is the equation. So times a cosine omega t. This variable, this product, omega squared times a, of course, represents the maximum value for the acceleration. Acceleration changes in time and in position, but it has its maximum. This is how we can calculate it. Or, if we use the previous equation, amplitude times frequency, yeah, amplitude times frequency, angular frequency times angular frequency is equal to this. This product is equal to V max. So A max is equal to V max times omega. The only equation we need to prove is this. We need to use the law of conservation of mechanical energy for that. So that's for the future. Any questions? So these are graphs. This is a summary. Everything related to that special case. Special case based on these three conditions. Equilibrium at zero, starts from rest, and initially was released from the positive location. In that case, these are equations we can always use. In general, well, of course, we can modify those equations. In general, here. In general, if the equilibrium is shifted and we don't release it from rest, or we just give it a kick and it starts moving. But again, the structure of the equations is the same. Still, these coefficients represent maximum values. Still, same angular frequency, same period, same regular frequency. What's this? Calculate V max and A max. Okay. V max equals A times omega, which is 6 times 0.0785. A max equals 6 times 85 squared. Question. Probably the last question for today. So please take a minute, enter your answer, because I will solve it for you too, so we would be on the same page before we leave this room. Also, before you leave this room, you should pick up your exam, if you're still here, and leave your signature, if you are here. And this is not a tricky question. No, not at all. We said that the function doesn't matter. We can always calculate that specific number, which would convert sine into cosine. This is what matters. So the amplitude is this. And the omega is that number which we observe right in front of t. Wherever it is, that's omega. And what we see is 3 pi. A pi is a part of the omega. The omega is always between t, time, and function. Now, of course, we can calculate the period, 2 pi over omega. And now you can also calculate all other variables in a way we just did here and there. Thank you very much. And now you can solve at least probably 4 different problems already of the first part of the third homework. So please, exams, signatures. Good morning. Do you know what Professor Duffy wants for today? He wants pressure. All right. So just keep everything back, yeah, like it was yesterday. Okay, yeah. Keep everything. Yes.
Sorry.
That's it.
I think there's a mistake.
Maybe. Maybe. I know it. But I need leave the room very quickly. So if you could
to the
wait or
hours room.
which is there.
Yeah.
Yeah, I'll be there in 10 minutes or so. Yes. Several people did that, and for almost everybody, I've changed it. Are you sure you emailed it to me? Well, first of all, please send an email one more time, okay? And if I replied, I should have changed it. But please send me an email, okay? All right, thank you.
My question 3 didn't send until I pressed send for 4. I must have missed the button. So.
Maybe you should Yeah, do better.
I guess you don't do laundry, but so you guys about the times that I turn my laptop page.
No.
My mom washed my lab coat because she was like, that was actually disgusting, and I'm like,
Yeah, my
because
mom.
I haven't washed it in 2 years.
Yeah, true.
Same. I washed my lap coat like 3 times.
I was like, mom,
I don't see any grade so far. I don't see any grade. And I've been sending you emails about this. you can, I don't know what you can't. I know what I can and I can't. There are rules and I will have to follow the rules literally. At first. And then what I see on the Webassign, I don't see any homework grade. And requirement for this course is
If I don't get the grade for homework one, I will homework two.
you already have no grade for homework 1 and you already have no grade for homework 2, which means you already have no grade for more than 50%. That's the problem. And I've been trying to reach you out. And now I need your paperwork. That's the only reason.